Assalamualaikum and very good day. I'm Dr. Hidayah from the School of Civil Engineering, Faculty of Engineering, University Technology Malaysia. First, I would like to welcome everyone to my lecture video. This video is for online learning for the course of Advanced Road Material. In this video, I will discuss on the rubberized asphalt. So stay with me. I hope this video will benefit you and others. In this video, we want to understand how rubber is used in asphalt. So basically, we will discuss on the overview of the rubberized asphalt, type of rubber used with asphalt, and finally on its production, application, and performance. Let's have a look on the overview of the rubberized asphalt in the road industry. Natural rubber technologies are becoming wider spread in numerous applications in enhancing its usage on various forms of products. Malaysia is the leading producer country of rubber after Thailand and Indonesia. Currently, rubber is harvested mainly in the form of latex tapped from rubber tree. In addition to its raw rubber compound, water and minor impurities such as proteins, resins are included in this latex form. Natural rubber with asphaltic materials is a great invention towards producing an admirable quality of asphalt paving roads. With its inherent chemical composition as elastomer kind of properties, this polymer modification can change the performance of current conventional asphalt paving roads, which is recently faced many issues against temperature changes and traffic loading. Consequences such as global market price of rubber turns in very uncertainty ways has encouraged the government to seek for an alternative utilization of the natural rubber to support the industry. Therefore, natural rubber is seen as a preference material to improve the quality of asphalt for road construction as well as to support the economic growth of the rubber industry. The natural rubber is made entirely from natural product. It is ecologically sustainable crop and contributes to the maintenance of the global carbon balance. It can be replaced naturally, which makes it renewable resource. Recycle or reclaim rubber, which refers to the production of this type of rubber, eliminates the build-up of waste in landfills, is manufactured at a low cost with low energy requirements, and perhaps most importantly, it is most economical of all rubber's options. This leads to the production of less expensive yet durable products that benefit consumers and the environment. So, is rubber eco-friendly? Yes, of course it's sustainable. However, when rubber is discarded and not managed carefully, only then the rubber can become harmful to the environment. Therefore, various application of rubber should be investigated further to fully utilize the rubber, and one of them is in the road industry. So, how the rubber is added to the asphalt mix? Like what we have discussed before on the modification concept, dry process refers to the process of adding rubber into the mixture as a small part of the aggregate or filler, rather than blending the rubber with the liquid asphalt. This process is normally applicable to hot mix asphalt applications with normal aggregate replacement of 1 to 3%. On the other hand, the wet process refers to blending or reacting the rubber with the liquid asphalt at elevated temperatures before incorporating the resulting binder for use in asphalt paving or surfacing application. Rubberized asphalt is a term applied to rubber modified asphalt with less than 15% by the total weight of the asphalt binder. So we can say both methods apply for asphalt road. These are some terminologies associated with the use of crumb rubber recycled from scrap tires in asphalt mixture using dry and wet methods. Basically, crumb rubber is a recycled rubber obtained by the mechanical grinding of scrap tires into small particles. The use of crumb rubber in asphalt mixtures can be traced back to the 1840s when natural rubber was first introduced into bitumen to enhance the binder's elastic properties. Since 1960s, researchers and engineers have used shredded tires in asphalt pavement. There are a few terminologies can be found related to crumb rubber modified asphalt mixtures. Some of the commonly used terminologies include asphalt rubber, rubber modified asphalt concrete, and rubberized asphalt. The differences in terminologies normally relate to the methods by which the mixture is prepared. Currently, there are two main processes by which crumb rubber is introduced into the asphalt mixture, namely the wet and dry process. The modification through the wet process is formulated to enhance the asphalt binder properties through the physical and chemical bonding of the asphalt binder and rubber at high temperatures. The end product of this method is termed asphalt rubber. In the dry process, the rubber is first blended with hot aggregates before it is intimately mixed with asphalt binder. This process essentially modifies the gap-graded mixture to which crumb rubber is added to substitute a portion of the aggregate component. The proportion of crumb rubber used varies from 1% to 3% of the total weight of the mixtures, or sometimes of the total weight of the aggregate. The end product of the dry process produces a mixture called rubber modified asphalt concrete or CRM mixture. There are several other terminologies associated with dry mixed rubber modified asphalt mixtures such as plastrite, generic, and chunk rubber technologies based on different aggregate gradation used for the rubberized asphalt mixture. So how about Malaysia? Tracking back at the history of rubberized road in Malaysia, we have started the fieldwork for decades, but seriously, studies on the potential of natural rubber just about a few years ago, and the results of the fieldworks still under monitoring. Let's see what we have done in Malaysia so far. If we can trace back the development of rubberized road in Malaysia, the chronology started in 1950s, and the biggest project of all time is in KLIA. It involves the use of different types of rubber, including crumb rubber, latex. Then recently, we look forward in using cup plum as modifier in asphalt binder. And currently, a few trial projects have been implemented in few states, which is under field monitoring. And this will determine the planning of the next stage of using rubber in road construction in Malaysia. So what exactly the difference between cup plum, crumb rubber, and latex? It seems like different types of rubber used in the asphalt. From the field observation, few things can be highlighted. The first one, in most application of the rubber, it is used to modify the asphalt binder prior to mixing with aggregate to produce rubberized asphalt mixture. Then, in other observation, for dry process application, when the rubber particles act as elastic aggregate, the fieldwork obtain low density mix as the rubber tends to resist compaction, especially when adding to the dense graded mix. And then from field observation, it is also noted that less sign of damage, particularly cracked, compared to the conventional asphalt. And the mix also is observed with high stiffness modulus, especially those modified asphalt binder. In terms of the production and construction, the initial paving costs increase up to 10 to 20% overall, but reduce in terms of the maintenance cost, meaning that detailed cost-benefit analysis should be conducted in evaluating the whole benefit of the implementation, including its contribution to the rubber industry. Okay, let's have a look on different types of rubber available or previously used in asphalt mixture. If we talk about rubber, it can be categorized into different types. Natural rubber contains of rubber particles, water, and contaminants extracted from the tree. It's either concentrated latex or coagulated latex, also known as cup lump, where the latex is allowed to coagulate in the cup and collected as naturally coagulated cup lump. Previously, people used to collect latex, but nowadays, the rubber tappers prefer to collect cup lump compared to concentrated latex, but the price is cheaper and the quality is a little bit lower than the concentrated latex. And then we have recycled rubber. This type of rubber is taken or processed from recycled tires to reduce mountainous of tires in landfill that can cause harm to the environment. The tires is ground up and turned into crumb, and this crumb basically a mix of natural and synthetic rubber that undergoing the process of vulcanization to strengthen the structure. The tires are reduced into various sizes through the ambient grinding or cryogenic process. Physically, it replicates the aggregate particles. And then the synthetic rubber is artificial elastomers made of raw materials from petroleum byproducts such as butadiene and styrene. So basically, there are different types of natural rubber available and named. Some of them are liquid natural rubber latex or field latex, rib smoked sheet, and natural rubber powder. If we look into composition, basically the natural rubber consists of polymer or isoprene, water, and minor impurities of organic compound. For latex, the rubber constitutes about 30 to 40% of the total compound as shown in the table. Recently, the use of natural rubber polymer such as cup lump rubber in asphalt has increased due to the fluctuation in natural rubber prices and the demand of modified asphalt. Considering that cup lump modified asphalt requires an estimated of 4.2 tons of coagulated rubber for every kilometer of road, wider application of the technology will help to stabilize the price of rubber. In Malaysia, the use of cup lump rubber was expected to increase the domestic usage of rubber by 10% annually. Okay, next, let's have a look on the application of crumb rubber, which is obtained from scrap tires in asphalt pavement. At one time, the push to recycle tires in asphalt seemed to mainly be just a means of getting rid pile of scrap tires. For many local authorities, their first experience with crumb rubber in asphalt resulted from the enforcement included in the Intermodal Surface Transportation Efficiency Act of 1993. This is to reuse the millions of scrap tires dumped every year in landfill that can cause many issues to health and environmental problems. But now, the emphasis of using tires in asphalt binder is to improve the pavement performance. For Crumb Rubber, it is made of natural and synthetic rubber, carbon black, fillers, and extender oils. This type of rubber can be used with asphalt as road materials due to its unique physical and chemical properties. Okay, let's have a look on the detailed compositions and how this composition can benefit the properties of the end product. First, it's a natural rubber. So this natural rubber provides greater elastic recovery and excellent physical strength, and also resilience and high resistance to tearing and abrasion. Its working temperature is between -50 to 100 degrees Celsius. However, the natural rubber is prone to oxidation problem. Okay, as you can see from the table, the content of natural rubber in car tires is a little bit lower compared to the truck tire. And based on the previous studies, the use of truck tires will improve the performance of the rubberized asphalt better than the car tires, which support that having more natural rubber content will improve the rubberized asphalt mixture. And then we have synthetic rubber. Synthetic rubber is a mixture of two or more monomers such as butadiene and styrene. For example, SBR, styrene butadiene rubber. It's a widespread application in car tires in order to improve thermal stability of the tire compound. Next is a carbon black. Carbon black is a type of reinforcing agent which is believed to add reinforcing properties to the asphalt binder. And then fillers. The function of fillers is to stiffen the rubber compound, but excessive use amount of fillers could cause a loss of rubbery properties. And then extender oils. The function of this type of oil is to plasticize the rubber polymer, making it softer and easier to process, like reducing the modulus. And finally, an antioxidant or stabilizer. So the function of stabilizer is to increase the durability because rubber polymers is highly susceptible to oxygen, which can result in brittleness, cracking, and degradation of the rubber compound. Okay, next is how the tires are processed. It is important to recognize that today, CRM or Crumb Rubber modifier is typically a highly controlled material. The process is no longer just grinding up a stockpile of old tires and adding the rubber to hot asphalt. The handling and shredding process is carefully planned and monitored to produce a clean and highly consistent rubber material. The crumb rubber is produced through a process of grinding rubber tires into very small particles. During the process, the tire's reinforcing wire and fiber is removed. The rubber particles are sieved into different sizes, and the resulting rubber particles are consistently sized and very clean. The ambient grinding process is currently the most common and most productive means of producing crumb rubber. The end product of the cracker mill is an irregularly shaped particle with a large surface area, spongy-like surface in various sizes, from very fine powder to big granules. Due to very high surface area, these rubber particles react with asphalt binder reasonably fast and increase viscosity. On the other hand, there is another method of grinding which is called cryogenic grinding. The process is accomplished at extremely low temperatures like -87 to -198 degrees of Celsius by submerging the scrap tire in nitrogen liquid. Below the glass transition temperature, the rubber is very brittle and easily fractured to the desired sizes. The surface of rubber obtained from cryogenic grinding is glass-like, with a lower surface area and elastic recovery compared to ambient granulated crumb rubber of similar gradation. It produces clean flat surfaces, which reduces the reaction rate with hot asphalt binder with low elastic recovery. In comparison, ambient granulated crumb rubber results in a higher binder viscosity than any of the modified binders produced with an equal amount of cryogenic crumb rubber. This is possible due to the very high surface area and irregular shape of the ambient rubber particles, which permits a faster reaction with the asphalt binder compared to the cryogenic rubber. The above explanation demonstrates that the method used to manufacture crumb rubber has an influence on the extent to which the properties are enhanced. This slide shows the different sizes of crumb rubber after the grinding process. Physical properties of the rubber, such as type, quantity, shape, gradation, are mentioned to affect the performance of rubber-modified asphalt mixtures. The size, shape, and texture of the rubber particles used to modify the mixtures vary with the proposed applications to ensure expected performance is achieved. Different sizes of crumb rubber produced for recycling purposes are shown in the figure. Rubber particles with irregular shapes and relatively high surface area are more likely to react with asphalt binder at high temperatures to produce a modified binder. Cubicle-shaped rubber particles with a relatively low surface area are typical of aggregates and desirable for the use in the dry process as an elastic aggregate, as they are easily integrated into the aggregate mix. On the other hand, the solid form of material can also be converted into oil for further application through pyrolysis. This process converts solid material at elevated temperature into oil with the absence of oxygen. This is a good option to reduce the solid waste material in landfill and recycle the materials for other application, specifically for waste tires. So through wet process, instead of using the fine rubber powder or granules in the asphalt binder, the pyrolysis oil also can be used for the modification. Next, let's have a look on the production, application, and performance of rubberized asphalt. Asphalt rubber is defined by American Society for Testing and Materials, ASTM, as a blend of hot paving grade asphalt binder, reclaimed tire rubber, and additives, in which the rubber content is at least 15% by weight of the liquid asphalt binder and has reacted to cause swelling of the rubber particles. The truly mixed crumb rubber and other components with hot asphalt binder interact at high temperature for designated period, typical minimums of 1 hour for the crumb rubber particles to swell and exchange oil with the asphalt binder. For the dry process, the rubber is added in the hot mixed asphalt and not considered to modify the binder. Although some interaction with rubber may occur in place over time through the absorption of the light fractions, rubber gradations have a range from coarse granules to fine powder size. So, under the wet process, different types of rubber can be mixed with the asphalt binder and improve its properties. However, there is an issue related to the wet process. which is referred to the storage stability issue. Basically, when any types of modifier is added to the asphalt, the target of that modification is to get a homogeneous blend. The difference in density and molecular structure can cause the phase separation to happen, particularly between top and bottom of the sample, as well as to prevent it stick to the wall of the tank. This is the issue happened in Malaysia when the Crumb Rubber was initially introduced few years ago in the asphalt binder without any modification to the mixing facilities. The problem could be minimized with proper selection of stirrer and temperature control and the addition of additives during storage for better pumpability or workability of the mix during both production and construction. But the challenge now is how to have available stock and production not rely on demand. Shelf life, potential of separation occur during shelf lives. These are something need to be investigated further. From the laboratory tests of previous studies, it was found that the addition of rubber in the asphalt binder will first reduce the penetration value, meaning that the mix become harder than the conventional asphalt binder. Then, the addition of the rubber increase softening point of the conventional asphalt binder, which gives less tendency to the binder to flow at high temperatures. This is beneficial with the current climatic changes where the temperature of the surrounding is getting higher, and that will also increase the temperature of the pavement. In other words, it will increase rutting resistance that change the conventional asphalt from PG 64 to PG 76. This will give better viscosity and better resistance against temperature susceptibility of the binder. As discussed in the previous video, higher viscosities is expected at high temperature to prevent rutting and lower viscosities at lower temperatures to prevent cracking problem. So what we can summarize from the advantages of Crumb Rubber modified asphalt binder is that adding Crumb Rubber to asphalt binder can contribute to improve rutting resistance, resist the thermal and low temperature cracking, provide better addition between aggregate and binder, and finally gives high flexibility and stability as well. While the utilization of Crumb Rubber in asphalt mixtures has significantly evolved in the past few decades, there are aspects that have been continuously studied to better explain the effect of rubber on asphalt mixture properties. One such aspect relates to the interaction between the rubber and bitumen, which is considered vital to better understand the concept of rubber modification in both wet and dry process methods. The term interaction used in this study refers to the diffusion of the lighter bitumen fraction, which is aromatic oils called maltines, into rubber particles, which can lead to the swelling of the rubber. The swelling of the rubber as a result of the rubber bitumen interaction is shown schematically in the figure. When rubber gets in contact with bitumen, it generally absorbs the maltine fraction that has low molecular weight and leaves the residual bitumen containing a higher portion of asphaltenes, or we can say there is a higher molecular weight which increases its viscosity. The maltine fraction diffuses in the rubber particles, increasing the dimensions of the rubber network until the final swelling is achieved. Factors such as the temperatures and time of rubber bitumen contact, chemical composition of the bitumen, rubber type and size were all found to affect the rate of rubber swelling. With sufficient heat and time, higher degree of interaction between the bitumen and rubber can be increased to cause depolymerization of the rubber particles. The lower the molecular weight of the Maltese fraction, the more readily it will diffuses into the rubber particles. It has been suggested that there is a greater degree of rubber bitumen interaction with greater enhanced properties in the wet process than the dry process, thereby making the wet process the preferred methods of modification. The rubber bitumen interaction in the wet process is well established as it is considered as a major reaction that occurs within the mixture. Next, we have a look on the rubber as an elastic aggregate when adding using the dry process method. The first figure in your left shows the illustration of rubber particles within a gap-graded asphalt, and then the next figures shows the illustration of rubber particles' elastic behavior before and after releasing the load. When the rubber particles under stress, they tend to deform and absorb the energy. But after the load is released, the rubber particles tend to release the energy as well. In general, the use of rubber as elastic aggregate is preferred in open and gap-graded mix rather than the dense-graded mix. In the dry process method, normally around 1% to 3% coarse rubber by weight of the total mixture is added to the aggregate gradation having size between 2 to 6 mm. The idea of adding the rubber particles is to substitute a small portion of aggregates with rubber for the rubber to function just like the aggregates but with additional benefits of elastic properties as illustrated in the figure. By limiting the reaction time between asphalt binder and the rubber particles, and to be exact, a coarse granulated rubber with low surface area, the rubber particles are able to retain their physical shape and rigidity. In a gap-graded mixture, the gaps provided between the fine and coarse aggregate is allocated to the rubber particles within the mixture. On the other hand, in a densely graded mixture, the aggregate gradation must be on the coarser side of the specification to allow for rubber modification. Initially, the dry mixing method incorporates crumb rubber into gap-graded mixture. The target is to control the effects of snow and ice on pavement surfaces. The rubberized asphalt mixture was expected to have the advantage of breaking up ice and providing better skid resistance during icy conditions than conventional asphalt mixture. Previous studies observed that incidence of ice cracking increased when the percentage of coarse rubber added to the mixture was increased. The theory discussed above was applied in the production of a mixture with enhanced elastic recovery properties under repeated loading. This enhanced the mixture's resistance against fatigue cracking. Previously, laboratory tests indicate major increases in fatigue life and crack reflection control due to an increased pavement flexibility. However, it was found later that the rubber particles can lose some of their elastic behavior at temperatures in the region of -6 degrees Celsius, resulting a reduce in fatigue life. So based on the aforementioned flexibility, rubber modification is considered to have potential to improve fatigue resistance and ice control in pavements. This slide shows the scanning image of coarse and fine rubber particles embedded within the asphalt mastic. SEM or scanning electron microscope of the rubberized specimens reveal the fine rubber particles to be well embedded within the mastic, while for the coarse rubber particles, A large gap was observed around the interfacial transition zone area in asphalt mixture as shown in the figure. This slide shows the X-ray CT machine for scanning the internal structure just like our body. Using this machine, we can view the distribution of the internal composition of asphalt mixture. This scanning technique uses the ability of short wavelength electromagnetic radiation called X-rays to penetrate objects by measuring the X-ray intensity before and after it passes through the object. By analyzing the image, we can characterize the distribution of the aggregate, mastic, and voids. As shown in the figure, the distribution of voids can be analyzed from top to the bottom of a compacted sample. Therefore, using the X-ray CT machine, the images of the internal structure of rubberized asphalt can be captured. This figure shows the internal distribution of the rubberized asphalt composition produced using the dry process method. The figure compares the core samples with different rubber sizes, which are fine and coarse rubber, and also rubber contents, which are 2 and 3% by weight of the aggregate. Previous studies found that the addition of crumb rubber content using dry process is very sensitive, with only 0.5% addition by weight of the aggregate can give a big difference in the final performance of the mix. In the images, the rubber particles can be identified by the dark grey coloured regions and the avoids are highlighted in red. It can be seen that both fine and coarse rubber fill the gaps provided in the gap-graded mix very well, and the presence of these gaps minimize the potential for specimens' density inconsistencies between replicates. From the images, the fine rubber particles appear to be well distributed within the mastic and around the aggregates particle, while the coarse rubber particles of the same content are clustered within the mixture. This is believed to be due to the comparatively easy mobility the small rubber particles have in comparison to the coarse rubber particles during laboratory specimen mixing and compaction. The coarse rubber particles within the mastic are thought to be prevented by the surrounding aggregates from freely separating from their clusters in spite of external mechanical intervention such as mixing and compaction. This slide compares the conventional asphalt and rubberized asphalt. The photos shows the deformed specimen after compression with minor dilation having occurred in its middle section and cracks evident on its surface. To summarize the findings, major changes in the air void's properties occurred in the control mixture, indicating that it was more susceptible to compressive damage than the rubberized mixtures. All the results appeared to confirm to the dilation phenomenon that occurred at the middle section of the specimen very well. Furthermore, at 3% rubber content, the sample has less damage than the damage caused to the control specimen. For example, severe damage was evident in the control specimen with microcracks initiated at the interfacial transition zone area following deformation, particularly for the control mixture. In contrast, for the rubberized mixture, specimen damage, which refers to the increase in air voids area, is evidenced by the separated air voids that evenly distributed within the specimen's cross-section. The cracks formed in the interfacial transition zone area were found less than those observed in the control mixture. Therefore, the study shows that the addition of rubber particles to the specimens reduced the crack growth. The same observation can also be clearly seen as the rubber content increased from 2% to 3%. This proves that the rubber particles may retard the process of crack propagation due to its ability to largely resist stress imposed by repetitive loading under fatigue. The above-mentioned fact is possible as rubber could help to reduce the dissipated energy as a result of hysteresis effect, as shown in the figure. This is because when the load is applied to elastic materials, there is no hysteresis loop, as shown in the figure, which means the absorbed energy is fully recovered. This effect describes that the energy stored in the material when it is compressed is dissipated in a form of heat that contributed by the internal friction. Therefore, in order to reduce the material's susceptibility to damage, the dissipated energy by the material during each loading cycle should be minimized. Through rubberized asphalt mixture, the phenomenon of dissipated energy within the mixture could be minimized and fractures can be prevented from propagating within the materials to cause specimen failure. The elastic contacts obviously provide higher ability of the specimen with rubber particles to absorb energy under the imposed stress before rupture. This is termed as material toughness, which is associated with the increments in strain. The material toughness can be calculated by measuring the area under the stress-strain curve. Higher material toughness results in greater materials resistant to fracture. The table lists energy absorption values for different materials, with rubber having the highest modulus of toughness and energy absorption compared to the wood and iron. Next, let's have a look on the facts about crack. This slide describes about the crack patterns, which are crack density, crack tortuosity, and the crack branching factor. Resistance to fracture can be correlated with these parameters, which are relevant in materials research, especially in describing the rubberized asphalt against crack. Details of each parameters can be seen from the figure. So what are the facts about cracks and how the mixed character improves its resistance against fracture? Basically, the greater the value of crack tortuosity of a material, the better the material's capability to resist crack growth. This is the case because the material is able to provide the choice crack path to prevent sudden catastrophic crack growth, which is known to result in spontaneous fatigue failure because a propagating crack always seeks the path of least resistance. In other words, the catastrophic crack growth is inhibited by crack blunting, whereby the plastic deformation prior to crack propagation is increased. By this means, cracks can be arrested and diverted, averting sudden failure of the materials. For a crack to propagate in the event of the aforementioned, the cleavage has to find the weakest path, and its fracture energy must exceed the cohesive strength of the materials at the crack tip zone. In this slide, all the specimens where a large number of cracks are present in the interfacial transition zone around the larger aggregate particles and mastic. This is believed to have been caused by insufficient bonding between the aggregates and the mastic. For control mixture, the main cracks are shown to have propagated through the binder and fines, whereas for rubberized mixtures, the rubber particles appear to have afforded to the resistance of crack growth. At the onset of catastrophic failure, when the cracks meet the rubber particles, crack tortuosity is increased through the allowance of greater elastic deformation, particularly near the crack tip, Before the cracks, select other weak paths to further propagate under the repetitive load cycles that could improve the material toughness. This is clearly shown in the figure, especially for the specimen with coarse rubber particles. This is supported by previous study who discovered that the crack tortuosity is an important variable affecting the fracture toughness of the material because it has the potential to prevent the localized stress intensity in the area of the crack tip from reaching a critical level where the catastrophic crack propagation occurs. Next, we have a look on the use of rubber, to be exact, crumb rubber, used within a stress-absorbing membrane layer or crack relief layer. It's an application of crumb rubber modified asphalt on the surface followed by the application of pre-treated aggregate. In this case, the addition of crumb rubber in asphalt binder has increased the viscosity at high temperature to provide better resistance against bleeding and very flexible at low temperature to give better resistance to thermal cracking and fatigue cracking. Others, the rubber reduced the aging potential or oxidation rate. This is the example of the placement and coring sample of concrete pavement with a thin layer of 25 mm thin overlay rubberized hot mix asphalt. This thin layer acts as stress-absorbing membrane to control the reflective cracking problem. This slide shows the photos of stress-absorbing membrane interlayer. After 8 years, the one with the crack relief layer has reduced the cracking potential. It contains high asphalt content, more than 12%, improved structural strength, impermeable, and resistance to fatigue, reflective and thermal cracking. This reflects the idea that we have discussed previously, where the elasticity of the rubber could improve asphalt properties in terms of absorbing and releasing the stress, which improve the material's toughness. Next is on the issues related to the use of rubber, which depends for the use in dry mix or wet mix. Of course, the pre-treatment is needed, for example, cup lump such as scraping process, the removal of water and contaminants, reduced size, and preheated prior mixing. Another problem is related to the potential of rubber to swell and resist compaction, but this one is more on the crumb rubber issues. Next, in terms of the production, which involve mixing temperature, which affect energy consumption, modification of existing machine, which could add another cost to the production, and storage stability, as well as to get the homogeneous blend. However, this is not a big problem with the right temperatures, additives, and proper storage technique. Next, in terms of construction-wise, low density or ability to achieve the target degree of compaction. This is more problematic related to dry process. Then, the field performance monitoring, long-term monitoring should be conducted for better evaluation of the mix under a real loading condition. And then, the cost, of course. The best way to do is to evaluate the life cycle cost. This include the cost of road construction, consists of design expenses, material extraction, construction equipment, maintenance and rehabilitation strategies, and operations over the entire service life. These are some highlights of what we have discussed on rubberized asphalt. It should be noted that the content and rubber properties determine the final mix performance. The modification technique is based on either modified bitumen or aggregate replacement. And then either it's cup lump or latex or crumb rubber, it should be pre-treated before used. For the mixture design guidelines, a few elements should be put under consideration, such as aggregate gradation, bitumen content, and air voids content. In dry process mix, normally the open graded and gap graded are more preferred, while for wet process mix, the modification is suitable for dense graded, open graded, and gap graded mixture. Finally, it should be noted that slight modifications in the mixing and compaction procedures is significant for better handling the mix and quality of the end product. Okay, that's all for Rubberized Asphalt. Thank you very much for watching. See you in the next video. Stay safe. Assalamualaikum.